Hello, I am Andreas.
I'm Devon.
I'm Omar.
I'm Vaughn. We are Team 1 working on the intelligent parking application with NAVC.
Our team is working on the intelligent parking application here on campus. The application will be available on Android and iOS devices, and it's aimed for students who commute to campus. And on completion of this application, they will be able to get up-to-date information and predictions on which parking lots are currently open, dependent on weather, school events, and traffic to help ease the flow of traffic throughout campus.
Since last semester, we've been breaking into understanding our predecessor's work. As of this past month, we've been able to roll out some changes to the application kickoff for work on finalizing.
As we worked a good amount of our story points, ending up splitting into subtasks, which could have been considered their own stories. In an effort to overcome this, our team agreed to rename and split apart some stories to better reflect our efforts.
As at the end of this iteration, we have completed 30 of our 41 story points. Currently, we have decided to push back our back-end security update, our weather widgets, and our current events tab. Today, we will showcase a hand-picked selection of our most impactful stories that we have worked on during this iteration.
Hello, my name is Devon Barrett. I work with Team 1, working with NAVC for our intelligent parking application. As far as tasks go, there are many tasks that have been completed for the iteration 2. However, the main key tasks or stories that I've been tasked with were running UI tests on a physical Android device, and not only that, but also developing a TensorFlow prediction model for our server to use. Now, to start off with, for UI testing on the front end with the Android physical device, with our team being so close to fulfilling all our current user stories, with special thanks to previous teams as well, we've emphasized the need to ensure that we deliver a working app by testing on a physical device. With that being said, I'd like to show off the ease of access that comes with testing on a physical device is astronomical. And I can show you also how I went through that as well. So by enabling developer options on a physical device, I was able to enable USB debugging. Fortunately, I didn't have to install any drivers for my specific phone model, so now all that was left was to establish a connection and install the current API into the phone. So to give you a brief demonstration, I'll plug my phone into the computer. And as you can see, all I would have to do is just install the current build of the API that we're using into the phone, and then I can make system tests on the front end and also verify some geolocations in the back end, which is what we've been doing for the majority of iteration 2. All that can be streamlined into an easygoing process and to where it's convenient for developers. So as a developer, I need convenience as I test front and back end features. So this is only the beginning to interactions with user experience in mind on the front end, for the simple fact that we do need to prepare for general versatility when releasing this product into the open market. And as you can see as well, there are certain buildings that are unmarked. So one of the focus for iteration 3 will be updating the user interface on the front end by manipulating geodata, importing custom icon images in our assets. But that's for that story point. And next on the list for story points was developing a TensorFlow prediction model. Uh, that story, as we've been collaborating with different teams, there's been a need to replace our current Python scripts that have been used to schedule and simulate predictions in a table with artificial data coming in from Firestore. Well, let me go back and say Firestore's data is not artificial, or it's not simulated, it's not dummy data. However, the scripts that are being used with Python for predictions are. So for developing a prediction model, we decided that an LSTM, or a long short-term memory model, will be well suited for the sequenced historical prediction problem. This iteration involved using local spreadsheets. So if I went into my model here, excuse the output, it's a lot. But going into our output here, so I'm just reading into a simple Excel file, a simple spreadsheet. This is just for versatility for now until iteration 3 comes around to where it's fully uh, developed for deployment. But again, this iteration involved using local spreadsheets for data collection that simulated the parking data to be found in Firestore. So I can also, zooming in, we have just lot names, total spots, percent occupied, etc., etc. These are things that we'd expect to be fed into Firestore. And after selecting that spreadsheet, that process data, or that data is being processed so that it can be later trained and formatted, defining our LSTM model. Now, this is where it really gets interesting. So taking a look at this output here, the main keywords to make note of are epoch and loss, right? So each epoch line shows that the training process, or it shows the training process of our LSTM model, whereas an epoch is just a full iteration over an entire data set. Our data samples are small right now, so the fluctuation, as you might have noticed, is widely variant, or there's a high variance. So the fluctuating loss value suggests that a high variance is going to be due to, again, that small data set size. But in our next iteration, 3, our team will work on communication with Firestore's database to collect more data received on campus. So in summary, the output demonstrates the complete workflow of our machine model. And it's far from perfect, but it's ready for testing with Firestore so that it's ultimately ready for predictions and deployment. But once this model receives more data samples from our ECE team or just from us as artificial data, we'll prepare for its deployment in iteration 3.
Hello, my name is Andres, and I'll be talking about things I worked on in iteration 2 regarding the story points I have completed. So I was tasked with investigating security requirements for our server and the backend. So for our server, we're working with Firebase and specifically like the rules part. There you go. The rules part and a little bit about Firebase security rules. Firebase security rules protect your data from malicious users. When you create a database instance or cloud storage bucket in Firebase console, you can choose to either deny access to our users, which is the lock mode, or grant access to our users, which is test mode. And currently right now we're in test mode, which is open access. As you can see here, allow read and write to any for the collections and documents in our database, which is not really recommended, but since we haven't deployed the app, it's okay. But moving closer to deployment and future iterations, this can be rewritten to either content owner access or a mix of public and private access, which I plan on updating these closer to time of deployment. Another thing I was tasked with was updating, not updating, but adding a constraint to this database, specifically regarding the open spots attribute or our open spots document, and that you were able to just update it to any value, even if it was greater than the size of that parking lot. So right here, as you can see, it will allow update if open spots is less than or equal to the size of that lot. I have not tested it. I need to set up a Firebase emulator or use the real-time database, and I haven't published it yet just because I don't want to publish it without testing it. So I plan on doing that in iteration 3. And the last thing I was tasked with doing was adding and verifying the parking lots on campus, which I really underestimated. but I gave each parking lot a 4-character unique ID, as you can see here, and I was able to get all of them and name them and then update that size. At first, we divided and conquered this, and we forced it, counted some lots, because I was unable to find any public information regarding like the space count of the lots. But then I reached out to facilities, and they're really helpful, and they gave me the information I needed regarding um, the sizes of the lots, and it was really good as well because we didn't really have trouble naming the lots, but we associated the lots with different buildings that were around it. Uh, for example, the West Stadium lot was a stadium lot, but some people would refer to it as like the hoop lot. So it was really helpful that we're both on the same page on that, and just because the names were the parking lots didn't have specific names. So yeah, I'll just show you a little bit of the lots: the gravel lot, the utility residential lot, playhouse lot, purple lot, the IM lot. So yeah, I was able to get all these in, and I've been working kind of hand in hand with Vaughn, um, just giving him the unique IDs for these lots, and he's been plotting them um, in the back end to physically create that lot on the app, and I'll let him talk more about that. Thank you.
Vaughn here. Before I speak on my main deliverable for this iteration, I'm going to walk through our file system and explain the structure of our application. During this iteration, I first set up a GitHub repository in order to facilitate sharing and version control among my teammates. There are two main file tiers to consider. The app file, which hosts the functions that run on the app's backend on the phone, and the server file, which receives, interprets, and pushes data to our Firebase, which communicates with the app. Mainly, I focused on editing inside the app file. During this iteration, I worked hand in hand with Andreas in order to find out how we could add new parking lots to the app. He figured out the Firebase side, which is mostly hosted inside this file, while I tackled the application side, which is hosted inside this file. At first, I looked through the library file to see if there were any sorts of functions that had anything to do with parking lots or where the parking lots were plotted inside the app. While looking through this, I discovered that the team was using some sort of get geodata and some sort of geodata file to draw polygons and color them onto the map. Using this knowledge, I navigated outside of here and went looking for a file that had geodata included. Lo and behold, I found one in the assets file titled geodata.json. Inside this file, you'll notice objects that contain coordinates. These coordinates correlate to drawn polygons on the phone's app. The only thing I needed to do in order to make new parking lots was have a way to get coordinates from the actual map. This was fairly easy as there was already a feature implemented that allowed me to click the app in order to get coordinates. Once I had these coordinates, all I needed to do was use a past parking lot as a template, empty out the coordinate section, and throw in my new coordinates to the file. This allowed me to add all the parking lots that I needed. I left out two parking lots, however, that being Foundation Hall's parking lot up here and the STEM Fit parking lot down here. This is because these parking lots were a tiny bit complex, being a merge of red parking spots and gold parking spots, and we had no way of knowing who was parking in the red spots and who was parking in the gold spots. So for now, we just left those out.
So this is the iOS simulator using Xcode. Currently, we have a prediction table that can capture what will happen in the short-term future. We plan on adding more features in the next few iterations for a more cross-platform functionality.